This is an extended presentation of complexity measures on the symmetric group and beyond for the 12th Innovations in Theoretical Computer Science Conference. This is joint work with Neta Dafni, Yuval Filmus, Noam Lifshitz, and Marc Vinyals. Let's start off with the fact that every function on the hypercube can be uniquely written in the Fourier basis, where the chi sub s's are the characters of the hypercube, and recall their definition below. The Fourier degree of a function f on the hypercube is defined as follows. So note that this Fourier analytic definition of degree coincides with polynomial notion of degree, where here we represent f as its real multilinear polynomial. Alternatively, we can define degree in terms of juntas. So recall that a junta is a function on the hypercube. In particular, a k junta is a function on the hypercube whose output depends on no more than k coordinates of the input. Okay, so juntas are canonical so-called low complexity functions. So recall that the space of real valued functions on the hypercube can be graded according to their Fourier levels, and the Fourier levels correspond to cardinalities of sets. And so these degree k functions are spanned by the characters whose corresponding sets have cardinality no more than k. Okay, recall that, of course, that Boolean functions can be computed by decision trees. And if you're unaware of this fact, then please pause the video and convince yourself that the decision tree below, in fact, computes the function f defined below. Okay, the decision tree complexity of a function f is the least possible depth of a decision tree that computes that function. There can be more than one decision tree that computes a function. Okay, so now let us compare and contrast decision tree complexity with degree. So if I have decision tree complexity k, then it's an easy exercise to show that my Fourier complexity for f has to be less than or equal to k. The converse is a bit harder. So if I have a function that has Fourier degree k, then a result of Nissan and Szigeti in 94 tells us that the decision tree complexity of f is polynomial in the Fourier complexity. Now, when we have such a relationship like this, we say that these two complexity measures are polynomially related. Okay. So up until recently, it wasn't known whether or not sensitivity was polynomially related to various other complexity measures in the analysis of Boolean functions. So let us go ahead and recall what sensitivity is again. So the local sensitivity on a input x is just the number of influential coordinates, and that's defined formally below. And sensitivity of f, we are just running over all bit strings and computing their local sensitivity and taking the max. Okay, so there are many other complexity measures, and we won't see but a small fraction of them in this talk. And all of the natural ones that folks study in the analysis of Boolean functions tend to be polynomially related to one another. So Huang's recent sensitivity results showed that sensitivity joined many of these other complexity measures in being in sharing this polynomial relation. Okay, so this work is not so much focused on the hypercube, but rather going beyond it. So recently there's been a lot of effort towards moving towards studying other combinatorial objects other than the hypercube. So below is a list. It's by no means comprehensive. It's just some results that over the past couple of years that I'm aware of that where the algebraic properties of certain more complicated combinatorial domains played a decisive role in a nice theoretical CS result. So I'll just leave these here for you to look at. But a natural question is since theoretical CS, since we're starting to consider other domains that are quite dissimilar from the hypercube, the question becomes, can we export our Boolean functions toolkit that we've honed on the hypercube? Can we export that to these other combinatorial domains? And of course, if one were to do this, you wouldn't want to do this in some sort of ad hoc fashion or case by case for each domain that you wish to consider. So the question becomes, is there a natural and a general framework for extending complexity measures on the hypercube to other combinatorial domains? And here's just a list of some combinatorial domains that come to mind. Okay, so one of the main contributions of this work is an abstract simplicial complex based framework that captures many, but not all of these combinatorial structures. And we'll get into that in the next slide. Okay, so the way this framework works is as follows. So first we declare a universe U of atomic symbols. Once we have U, we define the domain to be a collection X whose members are in subsets of some universe U, and where N is some fixed natural number. Okay, so the notion of a query is useful in this framework, as we saw it was for decision trees. So a subset Q of U, which intersects X in which intersects each member of our domain in exactly one point is called a query. Okay, and so with each domain, we associate a set fancy Q of allowed queries. Okay, so there's a number of other properties that one must define in order for various other complexity measures to be well defined, and we won't go into we won't get into these details, but please see our full version of the paper on the archive for a full definition of this abstract framework. So these three definitions here will suffice for the remainder of the talk. Okay, so let's see how we can model these various other combinatorial domains in terms of this abstract framework. So let's start with the hypercube. So we take a bit string and we're going to represent it as, we're going to represent each coordinate as a pair, namely the index and its bit value. So right, so we'll have one for each index, and there are n of those. So okay, let's move to permutations. So with permutations, for each permutation of the symmetric group, we're going to have a similar sort of data structure where I have a pair, and in the first coordinate, I'm going to have my symbol, I, and then in the second coordinate, I'm going to have where I gets mapped to by pi. And one can do a similar thing here for perfect matchings, where instead of a two tuple, we have a two set, and M of I just is the partner of I in the matching M. Okay, and so I think you get the idea here, but this framework allows us to capture many different combinatorial domains, and we'll only consider these three in this talk, but see the full version of the paper for other domains as well. Okay, so we're in a position to talk about our main result in this paper. And so the main result is that in this framework, in this abstract simplicial complex framework, we have natural notions of the following complexity measures. So we have good definitions for these. And we're also able to show that they're all polynomially related, like we have for the hypercube. And so we're able to show this for a number of domains. I won't explicitly list them all here, but the ones that we'll talk about in this talk mainly will revolve around the symmetric group. Okay, so as I've said before, we won't have time in this talk to even define most of these terms. Rather, we're going to focus on degree, decision tree complexity, and sensitivity. And before we move on, I want to say that there's much care needed in coming up with natural and correct definitions for many of these complexity measures. So although this is our main result, I would say that an equally important result is actually coming up with good definitions for these things, because there's a lot of different ways you can go about doing this. There's certainly enough rope to hang yourself, so to speak. And so it's you have to be quite careful that you're doing things correctly. Okay, so let's start with degree on arbitrary domains. So we're going to define a polynomial to be the following. And so this bracket notation here is, this is just an indicator function where we have a predicate inside the brackets that tells us whether or not it's a 0 or a 1. Okay, so the degree of a polynomial is the size of a largest s such that its coefficient is not equal to 0. So recall that these s's are subsets of our universe, and we're just looking at the largest non-zero one. Okay, and so the degree of let's say a Boolean function on our domain is just the least degree of a polynomial p, such that f of x equals p of x for all x in our domain. So I stress that we're saying a polynomial rather than the polynomial, because for certain domains you can have many polynomials representing the same function. And so we have to be a bit careful here in our definition. Okay, so what about Fourier degree now? So we saw that those two notions coincided for the hypercube, but we have to be very careful here for other domains. So first, let's let Rx just be the space of real valued functions on X. Now, this space is typically not going to have an orthonormal basis of characters like we have for the hypercube. And this is because these other domains, for starters, they aren't groups. They aren't abelian groups. And so it doesn't really, so we don't get this orthonormal basis of characters. But that's not to say that there isn't any algebra that we can hang our hat on, so to speak. So the way we've defined domains, it's done in such a way that we always have a permutation representation of a symmetric group acting on it. So let's consider that permutation representation. And so now, when we consider that representation, we can break this space up into Sn irreducibles. Okay, so these are irreducible representations of the symmetric group. And these are indexed by integer partitions of n. So we won't have time to talk about representation theory whatsoever, really, in this talk. So if you're unfamiliar with this, with irreducible representations, for this talk, it suffices to think of them as being like canonical vector spaces that are invariant under the action of the symmetric group and can't be decomposed further. Okay, so another thing that's a nice combinatorial correspondence here that we'll make use of is that integer partitions can be identified with Ferr's diagrams, which we can call shapes. Okay, so for instance, 541, that integer partition of 10 corresponds to this shape. Okay, so we're now in a position to talk about Fourier degree. And so Fourier degree is defined as follows. So n minus lambda 1. So the way to think about this is that this is simply the number of cells underneath the first row of lambda when we think of lambda as a Ferr's diagram. And so this P lambda, this is the orthogonal projection onto the lambda isotypic subspace. And so don't let lambda isotypic subspace scare you if you haven't seen representation theory. This just means that we're rounding up all the copies, all the vector spaces that are isomorphic to the irreducible representation of Sn that corresponds to lambda. So we round all those up, and that's what that means. Okay, so we're projecting F onto these isotypic subspaces, and if it's non-zero, we're counting the number of cells below its first row. And we're just taking the max of that. Okay, so this might seem to be a peculiar definition for degree, but it turns out that this is most definitely the right definition. But there's a really subtle question here that's very important. So we just gave two different definitions of degree. So I gave you a definition in terms of polynomials, and I gave you a definition now in terms of some sort of spectral, in spectral terminology, irreducible representations. So are these actually the same? And it turns out that they are, in fact, but it's not obvious. And this draws upon some results in algebraic combinatorics and extremal combinatorics, namely Erdős-Quadrato theory, but I'm afraid we won't have time to get into that here. Okay, so let's think back to our picture that we had that kind of described the spectral, gave us a spectral layout of real valued functions on the hypercube. So we get the same picture now for arbitrary domains, and only we're just replacing our subsets with integer partitions, and so it's very nice in that respect. So it's like the same picture you have in mind about spectral complexity. You can sort of just substitute in integer partitions, and more or less you have the right idea. Okay, so let's now talk about decision trees. Okay, so let us revisit how we did this in the hypercube. So recall that for a hypercube, my universe was just these tuples where I have an element of from 1 to n and a 0 or 1 in the next position. And we can define bit strings as n subsets of this universe U. And now my queries, remember, my queries have to intersect each of my members of my domain exactly once. And so my queries here for the hypercube are as follows. So clearly, I cannot be both 0 and 1 simultaneously. And so right. And so we can draw a decision tree here, and the internal nodes represent queries here, where we're looking at particular bits and querying whether or not they're 0 or 1. So now let's do the same for permutations. So for permutations, it's instructive to think of them as being bipartite matchings of a complete graph. And so here for my universe, the ticked symbols represent elements on the right partition, and the unticked symbols represent elements on the left partition. Okay, and so as we saw before, we can define, we can think of permutations as, in this regard. So there's X. And now for Q, for our set of allowed queries, it looks a bit, it's a little bit hard to parse at first. But if you stare at it closely enough, you'll see that because of the condition that if I have an element on the left partition, I can only have that single element on the left partition be matched to exactly one element on the right partition. Because this is it's a perfect matching. And so each one of these queries will intersect each of my elements in X exactly once. And this is precisely what we need for a query to be well defined. And so in this permutation land, my decision trees look something like this. And so here I've omitted a lot of nodes just to make the picture legible, but my queries are now of the form, what does, like, say, I get mapped to? Or what is the pre-image of K? Like, what maps to K? So those are the questions that those are the types of queries that are happening in decision trees for permutations. And so, so recall that our main result was that all these notions, decision tree complexity and Fourier complexity for, like, say, the symmetric group, they're polynomially related. So what this means is that if I have, let's say I have some function f on some real value function f over the space of real valued functions on permutations, and I know its Fourier degree. Well, if its Fourier degree is non-trivial, then what this means is that there's a non-trivial algorithm that can compute that function, namely through as a decision tree. So so I guess one of the open questions that we'll talk about later is whether or not we can find applications for this, and that would be really great. But it seems like there ought to be. But yeah, anyways, let's move on and talk about sensitivity. Okay, so we gave in the full version of our paper, we give a natural definition for sensitivity, but it's a bit technical. However, for permutations, we can state it pretty cleanly as follows. So we have local sensitivity as before, but instead of thinking about exclusive OR as our perturbation there, we're looking at transpositions. And so the local sensitivity is just going to be the maximum number of disjoint transpositions that have this property, of course. And the sensitivity, we're just going to be doing the same thing. We're looking at all elements of our domain, and we're taking the max local sensitivity. So there are alternative ways of defining sensitivity for the symmetric group, namely if you just get rid of the requirement that they be disjoint. But if you do this, then it is natural to consider in the analysis of Boolean functions, but it doesn't, you don't get nice polynomial, at least to my knowledge, you don't get nice polynomial relations to other complexity measures. So yeah, so there's a reason why we have defined local sensitivity in this way. Plays nice with all the other complexity measures. Okay, so here's a very natural question. So now that we have this definition of sensitivity, I mean, if we're showing that it's indeed polynomially related to these other complexity measures, then we need some sort of analog of Phong sensitivity theorem for permutations. And so, you know, how would you go about doing this? So, you know, the first thing, the first object to look at would be to stare at the transposition graph, where we have this is the graph where two permutations are adjacent if they differ by a single transposition. And it doesn't take too long to see that, you know, if you stare at this graph long enough, you'll notice that it has many large hypercubes as induced subgraphs. And so the fact that this object has many large hypercube sitting inside it. This kind of makes you wonder, okay, maybe we can just reduce this problem of deriving a sensitivity theorem for permutations to perhaps the hypercube. So that's the idea. So we want to reduce to the hypercube. Okay, so there's a very important definition that's going to for which the proof of everything for the sensitivity theorem is going to follow, and it's this notion of a pseudocharacter. So as it's defined here, it's not all that remarkable. We're just calling a function a pseudocharacter if it's a 0 plus or minus 1 valued function, but it's the way that we're going to use these types of functions is what gives them their namesake. So we're going to take functions like this and x. So in particular, if x is the symmetric group, we're going to take functions on the symmetric group that are 0 plus or minus 1 and have them masquerade as characters, so to speak. So we're going to see how that works. And by characters, I mean characters of the hypercube here. Okay, so a pseudocharacter chi is d hypercube inducing if the support of the support of chi can be partitioned into subsets ci, each of size 2d, and each of these accompanied with a bijection. So here's where this masquerading bit comes in, satisfying the following. Okay, so the first condition is that if I have A in the hypercube, the D hypercube, and I look at its neighbors, so these are all at Hamming distance 1, and I look at all of their images under phi sub I, and I look at the set difference, and I get 2, and this is for each of my neighbors. So from j equal to 1 to D. And we also want to require that if each of these set differences are all pairwise disjoint. And so so in other words, we say that phi sub I takes neighbors to disjoint neighbors. Okay, so you can pause the video and let that sink in. The second requirement is that if I take 2 elements of my D hypercube that are neighbors, and I take their image under phi sub I, and then I evaluate chi at these points, then I see that chi behaves like the parity character, which we're calling a chi D. So this is so this is what we mean by a pseudocharacter masquerading as a character. Okay, so this definition is a bit involved. So here's a example of this. So you can pause the video and convince yourself of the definition through this example. So this is an example of a 3 hypercube inducing pseudocharacter when our domain is S6, symmetric group on 6 symbols. Okay, so why are we bothering with these pseudocharacters? Okay, so, the reason why is because we have this nice lemma that is reminiscent of Huang's theorem. So if we have a Boolean function that has non-trivial correlation with one of these masquerading pseudocharacters, then we can bound the sensitivity of that function from below. And the square root of D, that should remind you of Huang's sensitivity theorem, where that D comes from the fact that the degree of the parity character is D. And so with Huang's sensitivity theorem in hand, showing that this lemma is not too difficult. And right, so we require one more definition. So we say that X is alpha witnessing if for each D, the space of degree at most D functions is spanned by a set X sub D of pseudocharacters. And each degree D pseudocharacter is D hypercube inducing for some D that's larger than alpha times D. Okay. So why do we come up with this definition? Well, we have a theorem that from which we can deduce Huang type sensitivity results. If X is alpha witnessing, then for every Boolean function f, we have that the sensitivity of f is bounded from below by the root of alpha times the degree of f. Right. Okay. So this. So we have all these. So we have this nice lemma from which we were able to deduce this nice theorem. And the question is, do these things actually exist? So like, can we find like alpha witnessing? Can we prove that these domains that we're interested in are alpha witnessing? Right. So let's just consider the symmetric group. So what should these x sub d's be? So in other words, like, is there a natural set of 0 plus or minus 1 valued functions on R Sn that span the degree d functions, or degree no greater than d functions, I should say. So at first you would be it seems like finding a needle in a haystack or something. But if you know some representation theory of the symmetric group, then there's a really natural family of functions that pops out. Namely, it's these things that are called lambda polytabloids, and namely these polytabloid functions that satisfy this condition that the number of cells below the first row is no greater than d. So so representation theory is guiding us to these XDs being these so-called these families of lambda polytabloids. And if you roll up your sleeves, you can show that each of these degree d lambda polytabloids is in fact d hypercube inducing for some d greater than d over 2. So here alpha is equal to 1/2. And hence these XDs are in fact alpha witnessing. And so and so the things that I've glossed over here are some of the main technical representation theoretical results that our paper draws upon. But I should say that it's all very, if you've had I would say if you had a course in representation theory, I think you would know everything you need to know to prove these types of results. Okay, and so we arrive at the following theorem. And so this is the sensitivity result for the symmetric group. And we were able to show this for a few other domains as well. I just stuck with the symmetric group for this talk.